So in the next section of this sheet, we are looking at problems where all we need to do is fill in the remaining particle. So this doesn't necessarily require that you know what type of decay is occurring, although it is good practice to identify the type of decay, but all we need to do is fill in the missing notation here. So on this first one, we're just going to look and see what numbers we need to make the mass number add up to our initial reactant and the atomic number add up to our initial reactant. Because we have this electron being released, that is a beta particle, so this is beta decay, and I'm going to try and remember to label them as we go through. This is beta decay, so we'll put the beta there. And so, of course, -1 plus what gives us 19? Well, that would be 20. And if you know that beta decay increases the atomic number by 1, then that's easy as well. So 42 and we need 0 plus 42 to get 42, so we'll put 42 at the top here. And now we just need to look up our element. And so we'll come over to our periodic table, and number 20 is calcium, so we'll fill in that chemical symbol, and that's all we need to do there. So moving on to number 8, we have a blank for the atomic number, so we're going to need to start by filling in that atomic number. So we need to find that element Pu on our periodic table. So we'll come over to our periodic table and start by finding that. And I actually think that that is actually a typo. I think the element that it's supposed to have there is Pa, which is number 91 on the periodic table, and I may have just copied that over wrong for my slide. So this is indeed supposed to be an A here, so I will fix that on my slide. Pa, and even if it is wrong on your sheet, we'll go ahead and correct that. Pa. And so, of course, we're looking at element number 91 for Pa there, and that is protactinium, Pa, 91. Once we fill that in, we can go ahead and look at what the other product of the alpha decay is. We know it's alpha decay because we have this helium particle here, which is the same as an alpha particle, so I'm going to put an alpha symbol to remind us that this is alpha decay. And we need to figure out our other product of this nuclear reaction. 91 minus 2 gives me... So the second one here, we have 239 as the mass number, but we are missing the atomic number for Pu, so we're going to have to come and look at our periodic table. Pu is right here. It's element number 94, so we can easily fill that atomic number in. 94, and then we just need to look at what the effects of the alpha decay are. I know it's alpha decay because of that helium right there, so this is alpha decay, and we need to say what plus 2 gives us 94. Well, that is atomic number 92, and then what plus 4 gives us 239. Well, that would be 235. So we have our mass number and our atomic number. We'll just have to come over to our periodic table and figure out what element is element number 92. And that, of course, is uranium. So we'll put uranium's chemical symbol there and move on to the next one. As you can see, this takes a lot less time when you already have most of the equation written. We are just filling in the blank here. On number 9, we have uranium-235 decaying, undergoing some sort of decay, so this time it gives us the isotope product of the decay, and we just need to figure out what type of particle is emitted along with that. So let's look at the difference in the masses, 92 and 90, so that means that the particle being emitted must have a factor of 2 change on its atomic number. And then if we look 235 to 231, that's a factor of 4 change for our mass number, which means that this is certainly an alpha particle. So I'll put that alpha symbol. So this is alpha decay here. And all we had to do is look at the change to the mass number and the atomic number. On number 10, we have 2 isotopes of hydrogen coming together. So I'll notice that they're both on the reactant side, and then we're just looking to see what the product of that nuclear reaction will be. So if we add those two isotopes together, 3 plus 1 gives us a new mass number of 4, and then 1 plus 1 gives us a mass number of 2. So this is now a helium atom. And two things coming together, we know that this is a fusion nuclear reaction. Fusion is when two smaller nuclei come together to form a larger nucleus. Moving on to number 11, we have lithium and then a neutron reacting together to form some products. Now I do think that there's a small mistake on our sheet here. These are two separate particles, so there should be a plus sign in between them, so I'm going to add that in. And then we need to figure out what is our isotope coming out of this nuclear reaction. So we have a couple things happening here. We have something being bombarded with a neutron, and then we will see what happens from there. So we do need to figure out the totals on both sides of this reaction. So on our kind of reactant side with the neutron and the lithium isotope coming together, that gives us a total mass of 7 and a total atomic number of 3. And then on the product side, what we already have is 4, and then 2 minus 1 gives us 1. So we do just need to add another particle in that will make the total mass and the total number of protons match what's on the reactant side. So because we know that the mass can't disappear, it has to go somewhere. And so when we add that particle in, we need to say 4 plus what will give us 7. Well, that would be 3. And then 1 plus what will give us 3? Well, that would be 2. So we know that this new particle has a mass of 3 and an atomic number of 2. So then we can look on our periodic table to determine what type of atom that would be. And of course, that's helium with an atomic number of 2. So this is not an alpha particle, because an alpha particle would have a mass number of 4, but it is a different isotope of helium. So in this decay equation, we're producing a beta particle, an alpha particle, and a new helium isotope in this reaction. So this would be fission, breaking apart of a larger nucleus here. So this is fission, using this neutron to break apart that lithium nucleus into 2 smaller nuclei. Up next, we have another reaction with a couple of reactants. So we need to add those up, so then we can then subtract out our product and figure out what the other product has to be. So we have aluminum and helium for a total mass of 27 plus 4, so 31, and then in a total number of protons or atomic number of 13 plus 2, so that's 15. So we need to match those numbers on the product side. Now we already have an atomic number of 15, so that means that the particle that we are adding in does not contribute to the atomic number, but it is going to contribute to the mass, because we need to go from 30 to 31. So we need 1 contribution to our mass, but something that does not affect the number of protons. So this has to be a neutron. So that's the only thing that we have that has a mass of 1 AMU, but has no charge and no effect on the atomic number. So if we add a neutron, it impacts the mass, but it does not impact our atomic number. So this has to be a neutron there. In the next problem, let's see, we have beryllium and hydrogen isotopes on our reactant side, and then we have helium as one of our products of our nuclear reaction, so we just need to know what the other product is. So we'll start by adding up our mass and protons on the reactant side. 9 plus 1 gives us 10, 4 plus 1 gives us 5, and then we just need to match those numbers on the product side. So 2 plus 3 more will give us 5. 4 plus 6 more will give us 10, and so we know that our particle has a mass of 6 and 3 protons. So that has to be an isotope of lithium with 3 protons, because we know the number of protons defines the identity of our atom. So 6 and 3, lithium is what fills in this blank correctly. Looking at number 14, we need to start by filling in the atomic number for potassium here, because we don't know how many protons it has. So we can do that based on our periodic table. Potassium is right here, and it has 19 protons. That's its atomic number. So we'll start filling in 19. And that is the only reactant. Potassium is breaking down by some sort of nuclear reaction. And so on the other side, we actually have not an electron, but a positron. So an electron that is positively charged. So it has almost no mass, but a positive 1 charge. So it is going to impact our atomic number, even though it won't impact our mass number overall. So 37 plus 0 will give us 37 mass. So I'll put 37 on top. And then what plus positive 1 will give us 19? Well, that would be 18. And so we're emitting a positron, which decreases our atomic number by 1. So now we are no longer potassium. We are the element with atomic number 18, which is argon. Ar is our chemical symbol here. In number 15, we have a whole bunch of products, like a whole bunch, 3 different ones. We'll need to add all those together. And then just a neutron on the reactant side right now, so we need to figure out what isotope we started with that then a fission reaction caused it to break down into all these different particles. Now notice that in front of the neutrons on the product side, we have a coefficient. That means that there's not just 1 neutron, but there are 3 of this particle on this side. So we need to multiply 3 times 1 and 3 times 0 when we take into consideration those numbers. So we'll start by doing that. So 142 plus 91. And I actually am going to use a calculator to make sure I get my math right here. So let's do 142 plus 91 plus 3. Whoops, 142 plus 91 plus 3. And that gets us our total mass of 236. That's 3 times 1 gave me a mass of 3 here. And then we need to get our total number of protons, which is 56 plus 36 plus 0. So 92 as our total atomic number. Now, on our reactant side, we just have 1 neutron. So we just have 1 piece of our mass and no protons so far. So on our reactant side, our isotope is going to need to have 92 protons and 1 less neutron than we have, or 1 less mass, which equivalates to 1 less neutron than we have on our product side. So 236 minus 1. So we started out with a mass of 235 in our original isotope. Okay, so now that we know that element number 92 is uranium. That is a commonly used nuclear fuel, is uranium-235. So uranium-235, and this of course is a fission reaction, breaking down 1 nucleus into several smaller nuclei. And also notice that we have a bunch of neutrons being given off, and this is one of the dangers of fission reactions, is that those extra neutrons can trigger chain reactions. And so this is one of the problems with using fission for nuclear power, is the danger of those chain reactions. In our next problem, let's see, we have uranium-238. And then an alpha particle being bombarded with an alpha particle. And then we'll look at the products that are formed. The only product currently there is a neutron, so we need to figure out what the other product will be. So we'll start by adding up our mass numbers and our atomic numbers on our reactant side. 238 plus 4 is 242. 92 plus 2 is 94. So we need to match that on the product side. So of course a neutron does not contribute to the atomic number, so the atomic number on the product side is going to be 94, but we already have a neutron that takes up one of those mass units, so instead of 242, our new isotope is going to have a mass number of 241. And if we look up element number 94 on our periodic table, that is Pu, plutonium. Plutonium, so we'll fill in plutonium's chemical symbol there.